Thanks for the invitation and for having me here today. I'm going to speak about invariances again. We had invariant sets, we had Tess's talk about equivariance. My talk is closer to Tess's talk. I'm going to talk about two different things, like one example of how you can design an invariant neural network, and then some theoretical thoughts on how invariances actually can help you in learning better. And this is joint work with some of my students and collaborators, so mostly led by Derek Lim, Josh Robinson, and Berus Tamasibi. All right, so let me first start with a setup of like what is invariant learning. You've probably seen this before, but just to make sure we're all on the same page. So in the standard learning setting, what we want is we have our training data pairs X, Y, and we want to estimate some function so that in expectation, some loss function is minimized or small at least. So we are basically looking for how to get that f hat, and f is our class of possible functions. Oops. And so what changes in invariant learning is that in addition, we know that the target function that we want to learn has some invariances. So invariance means if I take my data and I transform it by some group action, then the output of the model shouldn't change. So for any transformation G in that group G, capital G, my output shouldn't change. And so now I want to take this into account. I know that this is true, so I want to basically learn a model that already has these invariances built in. So I could learn them from the data, but if I know them, I could try to already put it into my model. So we'll assume that our model class has that class of such invariant functions. So just to show you some examples, here a simple example is translation invariance. So convolutional neural networks are translation invariant, meaning I have an object, I shift it around in my image, the meaning of the object doesn't change. Another invariance that we may care about is permutation. So when I'm learning functions over sets, the order in which I'm giving the elements in the set doesn't matter, just what kinds of items are in the set. I'm going to talk about graph learning. So in graphs, we also have permutation invariance. There, the thing is, I have to somehow input the adjacency matrix of that graph into my neural network. And so that means I'm imposing some kind of random order on my nodes. So, but the order of the nodes doesn't really matter. I can permute that adjacency matrix. It still encodes the same graph. So I want still the same output. And then there's other invariances like rotation and translation that Tess has talked about before. All right, so here's the outline of my talk. As I said, I'm going to talk about two things. So first, I want to talk about an example of how you can design an invariant model. So this is going to be a neural network on eigenvectors, and I'll argue why it's useful to have a neural network on eigenvectors. And then we'll talk a little bit about the theory of like, what do we actually gain from having that invariant network? All right, maybe I'll just use finger, that's a little more controlled. So first, let's talk about neural networks on eigenvectors. And the motivation why we actually started looking at this was because we were looking at learning on graphs. Graphs are kind of everywhere. They exist like in many different types of data. So it's very useful to have machine learning models that work on graphs. So these are just some examples. So what would a graph learning model do? There's actually various different things. So maybe one data point in your input is a graph, like in this molecule task, you want to predict properties of molecules. So I want a neural network whose input is like each data point is a graph and the output is like some prediction about that graph. Or maybe my input is a full one single big graph, like if I'm predicting interactions or which customer would buy like which product. And then what I want to predict is maybe links in this network, or maybe make a prediction about each node in that network. So both of these can be solved kind of with the same models. So there's many of these examples. So formally, the way this typically works is that we have some input graph. So we have the node set and the edge set, and that could be typically encoded as an adjacency matrix. Usually what we have is we have some additional features on the nodes, input features. So if you think about the molecule, this could be like the atoms and what kinds of bonds. We have some edge information. So I put this into my model, and if I want to make a prediction about a graph, what I want is that it just outputs like essentially a vector encoding the properties of that graph from which I can make a classification or whatever prediction. If I want a prediction about a node or a pair of nodes, I want something that's basically an embedding of a node, of all the possible nodes in the network. So what we typically want from this is, here's the formal version of the permutation invariance. So P is a permutation matrix. So now if I'm, as I said, I'm permuting the rows and columns of the adjacency matrix, I'm basically renumbering my nodes. The output shouldn't change. And so if we want node predictions, there should be an equivariance, meaning if I'm basically changing the order of the nodes, the outputs for each node, I have like the stack of outputs for one for each node, that should permute in the same order, that I basically know like corresponding input and output. So this is what we typically have for the graph neural networks, and the architectures that are typically used have this property of the permutation invariance. And so this is what it typically looks like. So I put in my adjacency matrix and I put in my node features, maybe some edge features, and then I have my prediction models. So typical models are message passing graph neural networks. So they are actually learning how to run a message passing algorithm. So in each layer, essentially, each node collects the current representations of its neighboring nodes, and it learns how to process them to update its own representation. So that's some learned aggregation function, some nonlinear function, or you could use a transformer, which kind of works as if the graph was fully connected. You have these pairwise interactions as well. So they're kind of related. So this does all the permutation invariance, but it has some limitations. And so often to make this work actually very well, you have to add some extra information. And I'll show you an example why this is the case. So for the transformer, that actually gives the transformer the knowledge about the graph structure. So this is called positional encodings. And so what it essentially encodes is some information about the location of each node in the graph. So something more about the global graph structure, where does it actually sit? But it's also needed for these message passing neural networks that just pass around messages, and they actually use the edge information that we have. So let me first show you why you would care about it. So if you do these message passing neural networks, one shortcoming is that they have actually very little information where kind of a message is coming from if you do multiple hops. And so basically they cannot distinguish something like this pair of these two graphs. So the first graph is actually two graphs, it's disconnected. The second one is that long loop. But that means they cannot do things like recognize, is there a triangle in the graph and things like that. So they are not so good at actually recognizing structural properties. So this is obviously like not very good if you think about predicting properties of molecules. It's not good for several other tasks where you actually rely on these structural properties. So we would like to add some capability for that as well. So we're adding these positional encodings, and now the question is, where do they come from? So basically positional encoding means for each node I'm adding in an extra vector as input to my neural network that gives it better capabilities. And so often these come from the eigenvectors of the graph Laplacian. So each eigenvector essentially gives me essentially one scalar for each node. So that gives me potentially that extra. So why the eigenvectors of the graph Laplacian? Because the graph Laplacian encodes a lot of structural information about the graph. So down there, these colorful plots, that's basically the some of the eigenvectors of that graph. So you see they kind of encode that clustering structure, they encode small motifs, etc. So that is actually kind of what we are looking for. So that's actually very useful. So that's a popular thing. It works actually well in practice. So let's add the spectral information. Let's add some additional eigenvector information, like the first k eigenvectors or so. We'll add them as input to our graph. So now the question arises, well, I could just, these are vectors, right? I can just use any neural network that works on vectors. But actually, they are special vectors. I know they are eigenvectors, and they have specific invariances. And the next slide, I'm going to show you those. So we have to be a little bit careful about maybe those invariances to make sure our networks are generalizing well. So the question is now we are inputting these eigenvectors. So now we actually need to think about what would a neural network look like on an eigenvector that processes these eigenvectors. So for instance, yeah, what about the invariances that we might want? And taking those into account, is it possible to sort of get a universal architecture for a neural network on eigenvectors that can parameterize any function that has these invariants? So let's talk a little bit about the invariances. The first one is sign flips. So if V is an eigenvector of a matrix, then minus V is also an eigenvector with the same eigenvalue. And now when you do these positional encodings, like depending on what solver you get it from, it could be like V or minus V. So you want your neural network essentially to be invariant to the sign flip. So again, we have sign invariance, but it's a very different one from the previous talk. So that's the first invariance. And again, this is needed for generalization, because if my neural network gives different outputs for V and minus V, then I can input the same graph and I get different outputs. That's not very robust. This mic is too heavy for me. All right. So the second invariance that we want is, it's basically a generalization of the first one. So beyond sign flips, if you have multiplicities of eigenvalues, you have multiple eigenvectors corresponding to the same eigenvalue. So they encode in a subspace, an eigenspace. So any basis of that subspace is a valid set of eigenvectors. So what we want is, we want our neural network to be invariant to change of basis. So basically, I'm multiplying on an orthogonal matrix to my set of basis vectors, and I want the neural network to be invariant to that. So these are the two invariants that we want. And now the slightly tricky thing is that we, of course, don't only have one eigenvector. We input a set of eigenvectors or a set of eigenspaces. So we sort of have this like as a product group invariance, essentially. So we need it like for each of them. And we may have that permutation invariance that we want because it's a graph neural network. So let's think a little bit about how could we make a neural network, set it up that has these desired invariants. So let's start simple. So this is the first result here is about like just a neural network that takes as input one eigenvector and has this sign flip invariance. So this is actually not yet necessarily a neural network. It just says that any function that has the sign invariance has to be of that particular form. So some nonlinear function phi and phi of v plus phi of minus v. It's very simple. It's pretty obvious that this is invariant to sign flips. But basically, any function that has this invariance can be encoded this way. And now if we think about designing a learnable function, we basically can learn this phi. And if we want it to be, in addition, permutation invariant, we would just make this phi also permutation invariant. So that gives us a model that can basically encode sign flip invariant functions. And if we make this phi like the function class rich enough, this is pretty much universal. So that's the first step. Now let's look at, okay, let's still go a little bigger. Let's try to do this basis invariance. But let's keep the sign flips in mind. So for basis invariance, here is what they would look like. So any function that has this invariance to the being multiplied by an orthogonal matrix, the change of basis has this form. It's basically can be written as this phi of VV transpose, where V is the matrix of my eigenvectors. So now it's actually a function from a matrix to vectors, but that phi again is some nonlinear function, so I could use some parameterization of a nonlinear function from matrices to vectors. And why is this, does this hold? So this direction is actually very obvious. If you just like basically plug in the Q and this is an orthogonal matrix, it just cancels out. So this one is actually very easy to see. And we can use it for graphs. We can build in the permutation equivariance as well if we want it to be a function for a graph. So again, if we now want to parameterize it for graphs, for instance, we could use just an MLP. So MLP is just a fully connected network. Or if we want the permutation invariance, we could use something that's called an invariant graph neural network. So it's basically some combination of equivariant linear layers and some pointwise nonlinearities. And so that would basically make it like compatible with graphs if we want that. Okay, so what did we achieve so far? So we basically designed a neural network architecture that is robust to sign flips and robust to these changes of bases. So that's like part of what we want. So what we also wanted was that these neural network architectures can take like a set of eigenvectors, because we want the first K, we don't only want the first one. And now this set of eigenvectors can have different eigenvalues. We can input them as well. So now we want, basically, we have actually sort of this invariance to a product group for each set of bases, essentially. We want that in there. So the question is, okay, how can we combine this? We have the neural networks like for a single sign, the eigenvector, or for like the eigenvectors for a single eigenvector value. Now we just need like to put them somehow and grow them, that we can do this set of eigenvectors. And this is sort of the main result of that work, is that you can do this again in a very simple form with this decomposition theorem. So what this says is, actually, to do this, really all you need is to have an architecture that's invariant to the sign flips, for instance. So that's the phi. So if this phi is invariant to sign flips, and this, you could think of this as phi of v1 to vl instead of x1. So if x is like the v's or the set of v's. Then basically I apply it to each of my eigenvectors individually, and then I just put them all together and aggregate that. So that's what this function rho is doing. So now what we can do is we can parameterize the functions rho and phi. And if we know that phi has the invariance we want, then basically the rho just combines it. The entire thing will be invariant. So this is good, because then we basically took care of the product group with that. The other thing is, we can also prove that with this, if you make like rho and phi strong enough, you can get basically universally approximate all functions that have these desired invariants. Okay, so this is sort of like some theoretical motivation for like how you could possibly parameterize a class of functions that has these invariances. Now we can try to translate this into neural network land, and I kind of already indicated with the different building blocks. So now our building blocks are this phi and this rho. And now by playing with it, basically we can get different neural network architectures out of this, but they all have the same global structure. So we first apply like the sort of eigenvector sign flip invariant one to each eigenvector individually, and then we aggregate it, or to each like subspace. So now we can just vary what is rho and what is phi. So what is rho? Rho, we could think of it as a function over a sequence, because we have the values of the eigenvalues, so we can sort them. That's like unique. We can do that. Or we could just think of it as a function of a set or a vector. So we can accordingly make this like a deep sets architecture. A transformer is like a set function, etc., or just an MLP. And then the phi function we could parameterize again, depending on whether we want to use it, say, for a graph, we want the permutation and equivariance or not. We can basically use a graph neural network or just like an MLP. So that just gives us like different architectures. We call them SignNet and BasisNet. So SignNet is the one that is just the sign flips, and BasisNet is the one that does the basis rotation invariance. Okay, so let me show you some empirical results, or actually theoretical and empirical. So we set up these architectures, and I said, well, actually adding this positional encodings and kind of doing it in a principled way, ideally that helps you a lot in like learning for graphs. So let's see, like, did we actually gain anything with this? For instance, so sort of what the first result is looking at is, well, we are using this spectral information. We are using these eigenvectors, and there have been graph neural networks before that worked on eigenvectors. So what they did was they basically learned a polynomial of the Laplacian. So what this first result says, that these networks can do anything that these spectral graph neural networks can do, and more. So they are like provably more powerful in their expressive power. What the second lemma says is that compares it to these message passing neural networks. And so what I told you was that these message passing neural networks, for instance, they cannot like this tell you like whether there's a triangle in the graph and things like that. So they cannot have these like structural properties so that they can recognize. So if you add the positional encoding and do it like process them in the way that I showed you, you can actually do this up to a certain extent. You won't be able to solve graph isomorphism, but you can do more of the structural recognition. So that's kind of for the theoretical part. It actually helps you probably in the expressiveness of learning for graphs. In practice, you see this reflected by getting like better results, especially for tasks where you need, like, you do some graph predictions and you need these structural features. So for instance, this is really a task that needs the structure. This is counting substructures. How many triangles do we have in the graph, etc. And what we are comparing is, so this is the error on the y-axis, no positional encoding, so just the vanilla graph neural network. This is a different way to do the positional encodings. And this is the way to actually, that really takes into account like how to properly do the invariances. So you see, it actually helps you. Like the positional encoding that per se helps you. That's like going from green to blue, and then blue to red is like doing it in the invariant way. And the second one is molecule regression tasks. So this is what I kind of argued, that if you want to recognize properties of molecules, having some ability to recognize the structural properties is important. So there's other tasks where this helps, like learning combinatorial optimization tasks also, but this is kind of like everything where you need the structure. It also helps for other tasks. So this is, it's actually more like a graphics task maybe, where you try to do texture completion. So you're predicting texture, and you can now basically like parameterize this CAD essentially as a mesh. So it's like a graph. And then you use, again, the eigenfunctions of the Laplace-Beltrami operator, which is kind of the equivalent of that graph Laplacian. And then you do the same thing. So you do the same SignNet architecture on that. And you do get improvements for these. So these are different metrics that you see in this table. Basically, it means that there's different metrics that mean slightly different things, but it means basically that you get improvements. All right, so this is what I wanted to tell you about, like an example of designing a neural network with invariances. And what I want to, the question I want to ask in the last part of my talk is basically that, well, I've kind of shown you that like learning with invariances makes the model learn better. And this is not something new. This is something that many people have observed in many examples. It makes intuitively a lot of sense. You're essentially reducing the degrees of freedom. Having observed like one data point is as if I've observed whatever its rotations as well. So it's kind of like a data augmentation implicitly. But the question is, do we also see this in theory? So how much, like if we think about how many samples do we need to get like a certain error? Can we see a reduction in the number of samples that we need in theory as well? So not in practice, we know it holds, but what about theory? So this is the formal setup. Essentially here, to make the theory tractable, I just look at essentially fixed neural networks or kernel methods. So it basically means we have some function space of smooth functions, and we're doing a regression task. This is just to make kind of the theory a little tractable. And we know that like the target function f star is invariant, so we want to learn an invariant function. So it is very, very well known that in general, sort of to get a certain error, so this is the error, this is the risk, basically the expected loss of my estimated function versus the true function. So I want to be close, so I want this to be small. It shrinks sort of as this function of the number of samples n. So it also depends on the dimension, and S is something that about the smoothness of the function. But it sort of depends on this, like that's kind of how it like shrinks. It's it's exponential in the dimension. That's the bad thing, and it's otherwise it's like a 1/n inside in it. So the question is, how would that change if I know that I have invariance? And there is some prior work on this, and essentially what this says is essentially the complexity of your function class for finite groups is divided by the size of the group. Or in other words, because that complexity sort of is on top of the fraction, it's as if I'm multiplying the number of observations by the size of the group, which is kind of sort of this thing, as I said, you observe one data point, you observe like transformations of that data. But so that work actually, it's a nice result. It's proved for learning on the sphere. and it's only for finite groups. So it's kind of limited. And essentially what we did in this work was we showed that this actually holds much more general, basically on arbitrary manifolds and for arbitrary groups, even infinite groups. So let me show you how this changes the sample complexity. So this is the one that I showed you before. And the important thing is kind of this volume of the manifold is sort of like the complexity here. And then you have the thing in the exponent. And so what changes if you know that your function class, like your functions have certain invariances, is two things. So the first thing is that green part. So now you actually, the complexity sort of your function class decreases. And now you have the volume of the quotient space here. And basically, if you don't know what this is, essentially think about basically you're dividing that term by the size of the group if you have a finite group. It's as if you're multiplying your number of samples by G because it's like size of the group times N. So that's the first reduction that you get. And the second reduction is in the dimensionality. So here we have the dimension essentially of the invariant, the quotient space. And that is as if I'm sort of subtracting the dimension of the group. So this is for infinite groups. This would apply. So we're getting two types of we're getting two types of reductions in the sample complexity. One is sort of, you can think of it as sort of multiplying the number of samples by the size of the group, and the other one is in the dimension in the exponent. Okay, that's basically what this says. And the green part is kind of generalizing what this other paper by Beatti et al., what they already showed. This is a paper from NYU. But it shows it basically for any learning on any manifold. So not only on the sphere, but also for other types of spaces where you're learning. And the exponent part is new because that basically comes from the invariant infinite groups. This result, so this is another theoretical result, it's also minimax optimal. So what these results say is the first one is the one I just showed you. It's the upper bound on the sample complexity. Error is upper bounded by this term. And what the second part says is that up to some constants, in the worst case, you will actually get this error. So you cannot actually do much better than that up to some constants. All right, so let me show you first some implications of this, and then I'll just show you like a very brief idea way how we actually prove this. So this is just going through the examples that I showed before. How much do you actually reduce the sample complexity? And here I'm just showing this as if you're essentially multiplying the number of observed data points. So in the first case, if we have permutations, if we have m items that we can permute, then it's like m factorial. The gain, if in the graphs, it's the same thing, it's permutation invariance. For the eigenvectors, the sign flips, we get a 2 to the m for m eigenvectors. So that's the factor that you're essentially multiplying your n by. And if you look at translation invariance, it's m squared for m by m images. And finally, if you look at 3D point clouds where you have invariance for translation and permutation and rotation, you get that's an infinite group because you have rotations. So you get the finite group gain and you get the infinite group gain by basically subtracting the dimensionality of the group. So you can do this thing like for other things as well. Basically just look at the size of the group and use these formulas that I showed before. Okay, so just like for a few minutes, let me just give a sketch sort of how do you actually prove this result. That's the hard part of the paper, essentially. So the idea is that you're looking at this error term that we want to control, and that's essentially governed by sort of the degrees of freedom or the size of the function space that you have. And the one way you can kind of look at this is by looking at the eigenfunctions of this Laplace-Beltrami operator, and those with how many not too small eigenvalues are there. That's kind of sort of the degrees of freedom. You can think of it that way. And now if I know I have invariances, I'm essentially reducing the degrees of freedom. So I'm sort of removing all the eigenfunctions that don't have these invariances. And then I look how many are there. So let me just show you one simple example of this. So let's say we are on a sphere. So you could think of the basis of the functions on a sphere as kind of the spherical harmonics. So it's these sine and cosine functions. And now if I say, okay, my group that I have is reflection about the y-axis. So I have sort of this line here, and like any points like that are reflections are identical. So then what happens is that the basis, that now I basically want the functions that are symmetric with respect to that. You basically, those are only the basically just those ones. So you're essentially canceling out about half of those basis functions. And that's kind of what we are looking for. How much do you reduce that number of bases? So that's the fraction of these functions. That's kind of what we're looking for. And now basically what the proof does is it looks like how many of these eigenfunctions are being removed. Like how many do you have that are invariant? And then this goes in basically by looking at like the variance and the approximation error. That's like where it comes into the actual error. And so the main result here is to show that like the number of these eigenfunctions that are invariant and have like an eigenvalue like bigger than a certain, actually smaller than a certain lambda, how is that bounded? And this is actually a result that exists like for general manifolds. It's called Weil's theorem, Weil's law. But now, and essentially what we proved here is Weil's law, but the thing is Weil's law for the quotient space, because the quotient space is the one that's the space of these invariances. So, and that quotient space of the M mod G, that's where all the complications come in, because this is like that theorem that existed holds for manifolds. So that thing is not necessarily a manifold. And even if it is a manifold, or you can kind of approximate it with a manifold, it may have some boundaries, and the like existing results need you need a boundary condition then to hold. So it's not that simple. So for instance, if you think about the example with a circle again, it's basically now you have two boundary points, these red points, and now you have to make sure that like everything works out with that. So that's like where the actual complexity is. All right, so let me conclude here. So I showed you two results. The first one was how you can design neural networks on eigenvectors that have desired invariances, with use especially for graph representation learning, but potentially much more broadly. And actually, there are other examples too where you can use it. And the second one is to show that also theoretically, so empirically, we know like invariances are great. They help us in learning, but in theory also, they actually do reduce sample complexity, and to actually think about how exactly that happens. Thank you.
Thank you very much, Stefanie. So time for questions.
Hi.
Yes.
Yeah. So in the empirical, or rather the practical implementation, how do you decide how many eigenvectors of the graph Laplacian to use as positional encodings?
Yeah, it's a little bit like in many things you have to trial and error, I'd say. And also, I guess, the efficiency. So computing a few eigenvectors is okay. Computing all of them, if you have a large graph, is very expensive. So you'll just use a few of them probably. It also I would say it also depends a bit on what kinds of patterns you think you're looking for. So the first eigenvector, I had this like image with essentially does the clustering, the big picture, like whatever, the big picture clusters of the graph. If you're looking for these motifs, you may have to take a few more. Maybe the clusters already like help you a lot in identifying where your messages come from. So it may be already giving you a good information, but typically a few. And then it depends how large are your graphs, and maybe you'll have to try a bit. So I don't have a good like lemma that says, okay, you should like exactly take that many for that particular task or so.
Yeah, because I was just kind of anticipating like, is there some kind of scaling of some kind of performance metrics, or but I guess you're saying that it could be problem dependent in some way.
I would think it's task dependent. There's probably something one can say about it, but I don't have like a formal result yet.
Thanks.
Stefanie over here. So is there a flip side of your last result? which is to say, I'm willing to do data augmentation, and you're just telling me that if I'm willing to pay a factor of m factorial in my data augmentation, I can essentially achieve the same. Is that a correct interpretation of your last result?
So actually, this is like if you're encoding it, right? You're not actually doing the data augmentation in the last result. It's just as if you had observed that data. So in the last result, I'm basically looking at that FineNet, BasisNet, and many other models where I'm encoding the invariances and saying, okay, for the same amount of like guaranteed error, how much less data would I need? So it's as if I had observed this data. You are right. In principle, you could say, well, I could also learn my invariances. And maybe if I had like so much more data, I could learn it. That's probably true. The other, I mean, up to whatever, like learning it. The thing is that you're not still not guaranteed the invariance with that data. So you're like probably like close, but it's still, because you've learned it, it's not all guaranteed everywhere. So especially if you have distribution shifts or so, that may like lead to trouble. If you're encoding it, it's gonna hold. So there's some other trade-offs. But also having like, whatever m factorial more data, it could be like quite a bit more data.
Right, thanks.
Yeah.
Thanks for the great talk. So I think I may have missed it, but so you had two terms for determining for a given group what the bounds are. One of them you had divided by the size of the group, but you said that was only for finite cases. What happens to that term in the infinite case? Like I know the exponent, you say like you can deal with the dimensionality of the group, but what happens for that term?
Yeah. So it's the volume of the quotient space.
Yeah.
I'm not exactly, I have to think about
it's
it.
okay. I can ask you offline too. Yeah, but I'd be really interested and also just so now I can provably say when people ask me like how much data is it equivalent to, I'd love to
we have the
that
one
number.
for the like equivalent, right? Yeah.
Awesome. I have another question, but I'll let other people.
Yeah, right here. Sorry. Thanks for the lovely talk. So I'm just trying, I think I got a little lost at the end. In the case that the quotient space is not a manifold, it has singularities, what results were you able to establish in that case?
Yeah. So basically, that theorem that I showed, and all the reductions still hold, even if it's not a manifold. So the idea is that you basically take this principal part. So you essentially approximate it with a manifold. And then you can show that, like, so in that case, the gains maybe not as big. So what I showed you, like in the sample reduction, it's like in the best case. So if you have like that approximation, it may be a bit smaller, and then it depends exactly on like the case by case thing. So that's what changes, but the result still holds. So you would basically, that would become that principal part.
You said you approximate it by a manifold. Do you cut out the singularities or do you smooth them out somehow, or?
So yeah, essentially it's like cutting them out.
Thanks.
So does it work? Okay, so I have a question about the neural network that you had for the eigenvectors. So I'm curious, how do you handle the scale invariance? Do you like normalize the eigenvectors to like same norm, or do you embed the scale invariance in a neural network?
Yeah, we don't embed it. So here we just assume they are kind of come out unit norm, as they often do. Yeah, so we don't especially enforce it in the.
Okay, thanks.
Hi, I have one more. I have a question. So I don't know if you're familiar with like Michael Bronstein's work on simplicial neural networks. They're sort of higher order analogs of graph neural networks. And I feel like they sort of address some of the same issues and problems that your spectral features do. So I'm just wondering if you compared to them, or if you have any intuition about the relationship.
Right, yeah, so there's the simplicial neural networks. There's some other higher order neural networks. People have thought about it. And that there's basically at least two routes you can go to address the shortcoming of the message passing neural networks. And so one is to go higher order, to say, okay, I'm actually looking at more than a node at a time. so that like I'm kind of looking at these bigger units and I have like isomorphism types, etc. And you can do it with the higher order Weisfeld-Lehman networks. You can do it with these, or you say, I'm basically adding more information to the nodes to make them more identifiable. So what you can show is that if all the nodes are essentially identifiable, so they have some unique ID, you can compute anything on the graph. So that's like the most powerful thing, even with message passing. The problem is to get this in a way that it's permutation invariant. So we didn't compare to those particular neural networks in our experiments. That like the trade-offs are typically that sometimes the higher order networks, so you can make them like very high order, they can be more and more powerful, they can be better than what I showed you. They often become very expensive because then you have to like do the higher order structure, so it becomes like big tensors or so. So they are slower, and the positional encodings kind of are pretty practical because it's still the same kind of simple, cheaper neural networks. So that's kind of the trade-offs.
Jim says you can go first. Thanks, Jim. I guess I have a question about just graph Laplacian eigenvectors in general, especially for smaller graphs. How smoothly do those subspaces change as I make small modifications to the graph? Do you have any intuition on that? And like whether, if it is smooth or is not smooth, like in which circumstances would you want that or not want that?
Yeah, that's a good question. And that's essentially one thing we are currently thinking about. So that's indeed the case that sometimes you can make a small modification and the eigenvectors change or the eigenvalues change a bit. And then that would lead, that would be something the network would be sensitive to in general. So you can address that. It's kind of, but you will lose a little bit of expressivity. So it's like a kind of a trade-off thing, how stable you want it to be. But that's a general problem with eigenvectors. Like there's some things known about how like the spectrum changes with changes in the graph. So that would be, still holding.
I have one more question if no one else does. So I know there's this literature on message passing and Weisfeld-Lehman at sort of how powerful is message passing. Is there an analogous question you can ask about your spectral GNNs to compare it to something canonical like Weisfeld-Lehman?
Yes. So you can compare it to the Weisfeld-Lehman hierarchy. And I don't know if I put it in a theorem. I think you get like 3 Weisfeld-Lehman. And for most of the models, it seems like that do some augmentation and things. That's kind of what you get, and maybe a little more, but you cannot prove 4 Weisfeld-Lehman. So it's kind of like somewhere in between. That's what you get. So yes, you can do like use basically that kind of measuring stick.